Welcome to the finale of our series on limits. In part 1, we talked about a couple of different limit laws, namely the limit addition law, and we also mentioned the limit constant law, and also the limit y equals x law. But today we're going to talk about a topic that's actually pretty similar, but it definitely adds a lot more depth into our knowledge on limits. Number 1, we're going to talk about the constant multiplication law. And that's pretty similar to our second law, which is the function multiplication law of limits. These ones are actually more closely related than you might think. But the last one we're going to talk about, of course, alongside multiplication, is the function division law. Although these laws do have their own purposes, the concept behind them is very simple, and it should not cause any fear whatsoever. So without further ado, let's take a look into it. So the constant multiplication law is actually very simple, and it states as follows. If you are taking the limit as x is approaching a number, and you have a function that is being multiplied by some constant c. Let's keep in note that c must be constant. Then all of this equals your constant times the limit of your function. So what's the logic behind this here? What is this basically saying? Basically what it's saying is if you have a function and you decide to scale it up before you take the limit, then mathematically, that is the same as you scaling it after you take the limit. So before us right here, I have a graph of two different lines. The yellow one is taking the limit like how we normally would, but the blue one is what happens when we apply the constant multiplication law. But since this is an easy one, let's just go ahead and plug in x equals 1 to 2x, and of course, 2 times 1 is 2. So that would be this point right there. But how about we take a look at this one up here? Limit as x approaches 1 of x, and then multiply by 2. Well, of course, as x approaches 1 of x, we already know this law. That's what we talked about last video. That would mean we approach 1, which is this point right there. However, it's not just 1, remember? We still have to include our 2 times our 1, which of course equals 2. And so what are we doing? We're raising this point up, and sure enough, it lands exactly on the same spot that our yellow equation landed on just a second ago. Now, this is one of the most basic examples you can look at, but you can trust no matter what the function is, this is going to be the result every single time. So rest assured, when you're dealing with limits and scaling, order does not matter. You can scale the limit first and then solve it, or you can solve the limit first and then scale it. Let's take a look at an example that's a little bit trickier. So the example we have here is limit as x approaches -4 of 3 times of g of x plus 2 times of f of x. Now if you saw part 1 of our laws of limits, you'll notice the addition law right there. It's pretty front and center. So we know we can go ahead and plug in our limit for each function. So now that we have our function broken down a little bit, let's go ahead and evaluate 3 times 2x first. So according to this law, we're able to move the constant 3 to the outside of our limit 2 times x like so. Then we can go ahead and evaluate our limit, which in doing so we get -8, and then multiply it by 3, where we get 24. Now let's do the exact same thing for our limit of f of x. All of this times 2 gives us our limit of 6x plus 16. Then plugging in x equals -4, all of this equals -8. So now that we found the limit of both of our functions, we're able to use both of those values and work out that the limit equals 16. Hopefully this explanation of the constant multiplication law helped. Let's get right into our next law. Alright, so next we need to take a look at the function multiplication law of limits. Now this law is also pretty simple, and it states, if I'm taking the limit as x approaches a number of a function f of x times g of x, then what that means is that I can take the limit of f of x times the limit of g of x. And just like last time, this law of limits is pretty straightforward. All it's saying is that you can multiply functions together first, or you can find the limit of each function first and then multiply afterwards. And either way, you're looking at getting the same answer regardless. And again, we could take a look at an example like we had last time with our x and our 2x example, but it plays out a little differently. So let's try it both ways. Okay, first let's go ahead and multiply these expressions together. X times 2x is 2x squared. So rationally, we should be able to find the limit as x approaches 2 of 2x squared. So this green function that I just sketched is our function 2x squared. If I plug in x equals 2 for x right here, our value approaches 8. So we should expect that from the other way around. What is the limit as x approaches 2 of 2x? Well, again, we can just plug in 2 for x, and we get 2 times 2, which equals 4. How about for the limit of x? Well, plug in 2 for x, and our answer literally is 2 equals 2. Pretty simple, but look at this. 4 times 2, if we do that, remember, the whole point is that we do our limits first. We multiply these together, guess what we get? We also get a value of 8, just like we saw in the last method. So similar to like what we saw in our constant multiplication law, it doesn't matter if you decide to take the limit first, or if you decide to multiply first. Either way will give you the same answer. Let's try it on a trickier example, shall we? Okay, so in this example, we're trying to find the limit as x approaches 1 of f of x times g of x. Now, if it were me, this is what I like to do, is I like to multiply the functions first and then finding the limit. To me, that's just a little bit easier, but it's totally up to you. So if I take our function x over x minus 1, and then multiply by 2x squared minus 2, I get the function x times 2x squared minus 2 over x minus 1. Now hold your horses. Before we start distributing the x, we don't want to quite do that just yet. And in fact, we actually want to do the opposite. Because here, according to our limit, if I plugged in x equals 1, then that would give us 1 minus 1, which equals 0. And of course, we do not want a denominator of 0. So to make sure that our function doesn't have an asymptote, we need to actually factor this out. So using whatever factoring method you'd like, you should get the function x times x minus 1 times 2x plus 2. Now hopefully you see why that I think multiplying it out first is a little easier. By multiplying first, we opened up the opportunity so that these factors can cancel out. So no longer does our function have x minus 1 over x minus 1. The real function that we're dealing with is x times 2x plus 2 or 2x squared plus 2x. Now that we have a denominator-free limit, now it is totally acceptable to plug in x equals 1 for x. And by doing that, we get 2 plus 2, which equals 4. And so the limit as x approaches 1 of our function f of x times the function g of x equals 4. And today we'll end off with the final law. Now the last law we're going to look at today is the function division law. And this law states, if you are taking the limit of two functions that are being divided, then that is the same as taking the limit of the numerator and then taking the limit of the denominator. And of all three of these rules that we looked at today, this is probably the most different, but it all lies on the same principle. Now with division, you have to be a little bit more careful though, because of course division, unlike multiplication or addition, is not commutative, meaning that you can't just move f of x and g of x where you please. F of x will always stay on top, and g of x will always stay on bottom. So that means their limits also have to stay on their proper sides. But it does rest in the fact that you can divide the functions first, or you can take the limits and then divide. So similar to last time, let's use a pretty simple example. So as you can clearly see, the green line is 1/2 x squared, and the yellow line is 1/2 x. And we want to try to find the limit as x approaches 4. And again, just like we did last time, let's do it both ways. So first, let's divide them first and then find the limit. But 1/2 x squared divided by 1/2 x, obviously, the 1/2s will cancel out, and that just leaves us with x squared over x, which cancels out the squared and the denominator, which gives us x. So in reality, all we're looking for is the limit as x approaches 4 of x. And we should already know this rule by heart. We've already seen it so much by this point. If we're approaching x equals 4, then our y value also approaches 4. So now let's try to do it the opposite way. First, we'll take the limit of 1/2 x squared. Of course, we could just use the constant multiplication rule like we used earlier, but it would just be easier to plug in 4 for x. And when we plug in 4 for x, we get a result of 8. Keep that in mind. Now, same thing for g of x. All we need to do is plug in 4 for x, and we get 2. And see, that's already a good sign. We have 8 and 2. And what do we know 8 divided by 2 is? Sure enough, 8 divided by 2 is also 4. So therefore, from this approach as well, we can also conclude that the limit of f of x divided by g of x equals 4. And this yet again just goes to show that it doesn't matter if you take the limit first or if you divide first. Either way, you'll still get the same answer. Let's apply this concept to a harder problem, and then we'll be good for today. In this example, we're looking at the limit as x approaches 0 of f of x divided by g of x. And so in an expression format, we have 10 to the x over x squared. Now, unless you know how to do this as division, which I don't even know how to do, so good luck, it's probably better that we take the limit of each side first and then divide the limits when it gets there. So let's apply the limit to 10 to the x first. Okay, now this one's an interesting one. So you have to know a little bit about the laws of exponents, but remember, we have to ask the question, do we have a denominator of 0, or are we taking the log of 0 or a negative number? In this case, if we're plugging in 0 for x, no we're not. So that just gives us 10 to the power of 0, which anything to the power of 0 is 1. So right off the bat, we have a pretty straightforward answer. But now let's take a look at the same limit, but applied to g of x. As x approaches 0, are we making any denominator 0? How about logs? In both cases, still no. So we're able to still plug it in, and we get a value of 0. So we can then plug in our values, 1 for f of x, and 0 for g of x, and uh-oh, we have a 0 in the denominator. Well, but you know what though? At this point, that's okay. Because we've evaluated both limits, there's nothing for us to do. All this means is that our limit as x approaches 0 of this function equals infinity. Now, how do I know it's not negative infinity? Well, remember, g of x is our denominator. It's x squared. And anytime you square any number, whether positive or negative, it's always going to be positive. So therefore, we can trust beyond the shadow of a doubt that our limit does approach infinity. So what are the key takeaways we've learned about our laws of limits so far? Well, if you ask me, I think it goes to show that they're all pretty similar. For now, that is. But really, I think the most important, all-encompassing aspect of all of this, whether you're talking about the constant multiplication law, the function multiplication law, or the function division law, they all are comprised of the same concept. And that is, limit order doesn't matter. And this makes it a lot easier for me because the less order I have to memorize, the easier my life's gonna be. Now, just to be clear, let's add a little side note here. Order can be important, especially if doing it one way affects your ability to do the rest of the problem. So keep it up, you're doing good, and stay tuned for part 3.